This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
Okay, good afternoon everyone. So as I mentioned in the lecture on Tuesday, we're going to start looking at the final section of the notes today. Okay, so the final section is really about feedback control system design in order to meet specifications. So it's about applying a lot of the analysis tools that we've been developing so far to actually figure out how to design a feedback control system rather than just analyse it. But before we start looking at the notes for part 4, I just want to talk a little bit about workshop 4, which you've all started this week and will be completing over the next 2 weeks. So hopefully what you've been doing this week for workshop 4 is building a model. Okay, the difference between the system that you're controlling in workshop 4 and the one that you played with in workshop 3 is that we now have, we're now interested in controlling the pendulum at the front of the little Lego robot in such a way that it remains in the upright position when there are disturbances acting on the bottom of it because of motion of the robot, and the pendulum is mounted in such a way that steering, so driving the drive wheels differentially to change the heading of the robot, will impart a force on the pendulum which will cause it to fall if you don't do anything, right? So there's a motor directly connected to the pendulum that can impart another force, right, to counteract the disturbance that acts on the pendulum due to motion of the robot in order to keep it in the upright position. So you can't quite do the step type tests that we used to build a model of the robot in workshop 3, okay, because the pendulum, at least in the upright position, is an unstable system. And if I put a step in, it would just, the response would, blow up effectively, okay? So hopefully what you've been doing is turning the pendulum upside down, okay, and then getting it to swing to produce some data, and you can build a model of the pendulum swinging, parameterized in a particular way, and again, hopefully you've gone through the process of adjusting the parameters until the simulated behaviour matches the data, right, as a way of doing system identification of the model. Okay, so what you'll be doing in the next couple of weeks is looking at control design, okay, for the motor that drives the pendulum. Of course, the way that the model has been identified, you've effectively identified the nonlinear model, all right? You're going to have to now linearise the model about the upright position, okay? And as we've seen before, when you linearise a pendulum about the upright position, you end up with unstable dynamics, all right? And you should end up with a transfer function that will be some constant, and it will have 2 poles, okay? It'll have one stable pole at s equals minus p1 and one unstable pole at s equals minus S equals plus P2. All right? So what we're trying to do, this is really our plant model. Right, maybe I shouldn't use C as the constant to avoid confusion. Let's call it M, okay? And what we're trying to do is design a controller transfer function, okay, such that the closed loop system exhibits desired behaviour, okay? And we might have input disturbances, output disturbances. Our reference is really 0 because we want to keep the angular position of the pendulum in the upright position, right? And that will correspond to an angle of 0, okay? If we define 0 to be the angle of the upright position. Right, so the steering of the car or you flicking the top of the pendulum is like injecting these signals here. Right, it's the job of the controller to measure the position of the pendulum, okay, and process the error relative to the reference, which will be 0, to take corrective action to reject those disturbances. Okay, so that's the control design problem, and it's a bit trickier than the control design problem in workshop 3, mainly because we have an unstable system. Okay. All right. So let's think about, what might happen if we just use a controller here like the one from workshop 3. All right, in other words, just a proportional gain controller, just a constant gain in here. So it does the same thing at all frequencies. Well, to get an understanding of that, you can think about the root locus plot. Okay. And what you should be seeing is that P2, all right, is closer to the imaginary axis than minus P1. All right, so P2 is the unstable pole, okay? Minus P1 is the stable pole, and you should see that P2 is closer to the imaginary axis than minus P1. All right? So let's think about what happens when we just put C of S equals to a constant. Well, the root locus analysis tools that we've developed will suggest that for very small values of K, all right, we'll get 2 closed loop poles that are close to the open loop poles, right? So one here and one here. And as we increase K from 0, this one will move this way and this one will move this way. Okay. Eventually, for sufficiently large K, this one here in the right half plane will cross over into the left half plane. All right, so we need enough gain here to be able to stabilise the system. Right? Eventually, these 2 poles will meet, and when they meet, they'll split apart, and they will go towards the zeros in infinity along asymptotes with angles pi on 2 and minus pi on 2. All right? Now, you'll find that this pole here is not that much closer to the imaginary axis than this one here. And as such, the asymptotes will lie very close to the imaginary axis. All right? And to get sufficiently high gain so that the open loop transfer function is sufficiently large where the disturbance have significant energy, you'll end up with a closed loop system that is very poorly damped. You'll end up with having to put the poles up here and here, right? Because we want to choose this gain also such that the crossover frequency of the open loop transfer function, which is just the product of the plant and controller transfer functions, to have a sufficiently high crossover frequency, because the type of disturbance we're putting in here is a periodic disturbance. We're making the car swing like this, right? So it's like putting an oscillating disturbance in, all right? That'll have its energy at a particular frequency. In order to reject that frequency, we've seen we've got to have sufficiently high open loop gain at that frequency, right? That will make the sensitivity function, okay, small at that frequency, so that the output is insensitive to that disturbance, okay? So you're going to have very high gain to make that happen. If you look at the Bode plot of the open loop plant, all right, it's going to be have a magnitude plot that looks like this, okay, where the gain at DC is actually less than 1. All right, so we're going to have to lift the gain up a lot, all right, in order to meet the disturbance rejection requirements. And in fact, you need to lift the gain up in order to stabilise the system anyway, right? Create an anti-clockwise encirclement of the Nyquist plot as required to stabilise the system with an unstable pole, right? But the main reason for needing lots of gain, more than is required to just stabilise, is so that we can reject the periodic disturbance coming in, all right? And if you use just a proportional gain controller, you'll end up with a very poorly damped closed loop, all right? You won't be able to meet, and that will correspond to having a very poor phase margin, right? If we look at the phase plot that you should get for this unstable system, right, so this is the magnitude of G. The phase of G will be something that looks like this. It'll start at minus pi, right, because of the unstable pole, right, and that contributes phase that goes up like this, right, up to minus pi on 2. All right, the stable pole does this slightly further to the right, right, which corresponds to, you know, it being further away from the imaginary axis than this one. Okay, so overall the phase that we're getting will be something like this. It'll hang around minus pi, right, and how much this pops up here will depend on how far this is from the imaginary axis relative to how far this is from the imaginary axis, because that determines where this kicks up and where this kicks down. All right? So we're going to increase the gain, you know, bring everything up. That'll give us a crossover frequency here, and you're going to get a terrible phase margin, right? Because, you know, in practice, this guy is not that much further away from the imaginary axis from this guy. So the phase of the open loop plant without any compensation never pops up much further than minus pi. Okay, so in order to meet the specifications, you know, we're going to have to use a more sophisticated controller than just proportional gain. All right, let's think about for a minute how we might get better damping. Right, this is poor damping because when these meet, they just split apart. Right, and increasing the gain while it moves the crossover frequency to the right, extending the range of frequencies over which the complementary sensitivity function is 1, because the phase margin is so poor, as you continue to move it further and further right, it peaks up more. All right, and so you're not actually getting any faster, you're just getting more oscillations. All right, so what we want to do is somehow bring these asymptotes further to the left. That's how we're going to improve the damping. Why is the damping associated with the pole here bad? Because the imaginary part is much bigger than the real part. That's poor damping. Good damping is where the real part's bigger than the imaginary part. Okay? So if we could do something by choosing a different controller to, you know, move these further into the left half plane, we should get better damped response. Right, which should be consistent with having a bigger phase margin, as we've seen. Right, there's a relationship between how much peaking we get in the complementary sensitivity function and sensitivity function, and the phase margin. Right, if you know a function that looks like this and has peaking and then rolls off, that's like classical second order dynamics, and the bigger the peaking there, the worse the damping, right? So how can we get these into the left half plane more? Well, we need something that's going to pull the phase up, right? And in order to just have two asymptotes corresponding to two zeros in infinity, we want to pull the phase up without changing the relative degree, right? Because the number of asymptotes we get here is related to the relative degree. So we want to keep the relative degree 2, so we've only got two asymptotes. And we want something that's going to pull the phase up to reduce the amount of peaking that we get so that we get a better damped response. Yep?
Why do you want the relative degree to be 2?
Well, just to keep things simple for the minute. Right, just for the sake of argument. Right? Well, if you did something and put more, if you changed it to become relative degree 3, right, then for large gain, right, I'm going to end up with poles in the right half plane. So it's going to, relative degree 3 is going to make things trickier to manage because I'm going to have an upper bound on the gain, because if I don't, I'm going to eventually end up with poles in the right half plane if I've got relative degree 3.
Why not 1? Why not cancel one of the poles and get 1?
Okay, but then my controller won't be proper.
Yeah, it wouldn't be here. Yeah, you're right.
Right? All trade-offs, right? If this is the only thing you've learnt in the whole course, I'm happy, right? Engineering is about trade-offs. There's never one way of doing something, as we'll just see now. There's never, ever just one way of doing something. But, you do something with this hand and you'll pay for it with this hand, okay? So let's just try to keep, if I use a proper controller, I'm going to get an open loop transfer function that has relative degree 2 or more. So let's just keep the relative degree the same as the open loop plant. All right? How am I going to push the phase up? Well, I'm going to need to have a 0, right? A 0 will contribute positive phase that will be added to the minus pi to bring it closer to 0. All right, so let's think about, putting a 0 in. So let's put a 0 in and do what you suggest. Cancel one of the poles, right? All right, so we've got this guy here. Let's do this, and let's put a 0 in and put it really up close. So it's kind of like cancelling it. All right? But then we wouldn't have a proper controller. Okay? So let's put another one in. Let's put a pole in to make sure that the controller's proper so that I can implement it. Right? So let's put it there. Okay? If I put it here, all right, the phase due to these guys will be something that's always positive, right? The phase of my compensator will be something that goes up, right, at, if that's a Z, at about Z, right? It'll go up towards pi on 2, all right? And this guy here will make the phase go down, but it'll kick down further to the right, okay, because that's a larger in magnitude number than this. Okay, so overall, it's going to add positive phase everywhere, right, which is what I want to do here to get this up, to get a better phase margin. Okay. Now, we can understand what's happening also in terms of the root locus, right? So we're going to use a controller with a 0 here and a pole here, right? So we're going to use a controller that looks like K S plus Z on S plus P3. And there's P3. Okay? Then for small values of K, I'm going to end up with 3 closed loop poles, right? Why? Because I've got 3 open loop ones, right? And one will be here, one will be here, and one will be here. Okay, as I increase K, this one will move towards the 0, okay? This one will move this way, this one will move this way, right? Eventually they meet again, but when they meet, they split apart and they'll go towards zeros at infinity along asymptotes. Where will the asymptotes now be, right? Well, the asymptotes, remember, are anchored at a point sigma, which is equal to the sum of the poles minus the sum of the zeros divided by the relative degree, which is just 2. So what I've done is I have added these two in to this formula, right, relative to what I had to do up here. Okay, so what have I added in here compared to what was already there before, right? These two are almost as close as each other to the imaginary axis, which made this sum close to 0, right, which is why the asymptotes ended up being close to the imaginary axis here, right? What I'm now going to add here is something that's very negative, right? And then I'm taking away something that's negative, right? So that's actually adding something positive to this sum, but what I'm taking away due to this is more negative, right? So the effect is the asymptotes are pulled to the left, giving me better damping. All right? Now, I could have put the 0 here, right, on the other side, and if I put the 0 here, then that pole would just come towards the 0. Let's do it. This guy, got this guy, I could have put the 0 there, right, and the other pole here. Then what would happen is this guy would come to here, like this. These would come together, and they would split apart and go to asymptotes like that, right? Still, the same sort of thing happens. The overall effect compared to what we were originally doing with just a constant gain controller is to move all of this stuff further to the left. And by moving all of this stuff further to the left, you get a better damp response because I'm increasing the real part of the closed loop poles, right? Poor damping here is due to the imaginary part being much larger than the real part, okay? So, you're going to have to use a compensator that does something like this in order to meet the specifications. Yep. Don't know. Figure it out. Right? Look, I've designed these workshops so that there's not just one answer. I don't want there to be one answer. Right? I want you to explore different possibilities for things. Right? Now, you might go nuts and say, well, I don't want to just increase the gain like this. I want to make sure that there's infinite gain at 0 frequency, because I know if I've got infinite gain at 0 frequency, I can set the reference to be a constant and I'll get 0 error in steady state. So what might we have to do there? Well, you could do something like this. Right, here's my unstable open loop pole. Here's my stable open loop pole from the plant. Now I'm going to put some extra stuff in from the controller. I'm going to put a pole at 0. Why? Because that gives me infinite gain at 0 frequency, as required for 0 steady state error for a step reference. Okay? Now, if I just put that in, I've got a relative degree 3 system, and increasing the gain doesn't even lead to closed loop stability in this case, right? So I'm going to have to, put some more stuff into the controller, okay? And so what else could I, what could I do? Well, for example, I could put a 0 in here, all right? And I could put a 0 in here, but now my controller's not proper because my controller has 1 pole and 2 zeros. All right? So now let's just, given that it seems like in this particular situation it's better to have some phase lead, let's put the extra pole for the controller that makes it proper way over to the left here. We've just seen that doing stuff like this pulls stuff into the left half plane to give you better damping. All right? What's the root locus plot going to look like? Right? Well, this is going to be part of the root locus, right? You're going to start off with two of the closed loop poles here and here, and they're going to come together as we increase the gain, which is another parameter in our controller, right? This one's going to move towards here, all right? These ones are going to split apart, and if you make the gain sufficiently large, they'll come around, as we've seen before, right? Come together, one will go that way, one will come this way, and these ones will split apart, right? These things are so far away from the imaginary axis that you really have to be way up here to get bad damping in order for the imaginary part to start becoming bigger than the real part. All right? So, we've now seen that we can, get zero steady state error, and if we put the other zeros and poles of the controller in the right spot, we could end up with a situation where the closed loop poles are all real. And it's only if I make the gain bigger than a certain amount that I'll end up having, oscillatory second-order dynamics, underdamped second-order dynamics. All right, so playing around with these root locus type plots is useful from the perspective of identifying the structure of the controller that may be required to meet performance specifications. Right? This guy is a lag compensator. This guy is a lead compensator. All I've done is I've used a combination of a lag and lead compensator. If I didn't have that pole there, what I'd have is a PID compensator. Right? I think it's far more important to understand in these sorts of terms what's happening than to know what these things are called. Right? Which is, in fact, the point of going through this example now, because the first part of, part 4 of the notes is about identifying different types of compensators, right? But it's not you just use one type of compensator. Here I've put two together to achieve what I want. Okay? Here's use of a tool that we've learnt about in the context of analysis, but now being used to inform design. Not complete design, like I'm not saying exactly where I'm putting these things, right? But it's giving me a controller structure that is parameterized. It's parameterized by the location of this zero. It's parameterized by the location of this zero and this pole, right? It's parameterized by the gain that I'm adjusting to move the closed loop poles around, on the locus of closed loop poles in the way shown. Okay? So you're meant to be exploring all of these different possibilities in doing workshop 4. All right? You're definitely going to need lead compensation for the reason I outlined before. The open loop plant, right, has pretty much flat phase across frequency, right? And it's very close to minus pi, which is consistent with the root locus plot here when we're just using a constant gain controller, giving you poles that are always very close to the imaginary axis. Poor damping. All right? So you're definitely going to need the lead part. And if you really want to, go berserk, you can start considering stuff like this. All right? But this is your first taste of seeing how some analysis tools can be used to inform design decisions. We're trying to design something here, right? And these analysis tools are helping us, in this case, identify structure as a starting point. Make sense? The other thing to consider when doing workshop 4 is that the Lego motors are really shitty, right? Especially the one that's driving the pendulum. The two that are driving the back wheels are actually not too bad, but the one driving the pendulum is actually different to the two that are driving the wheels. Okay? It has much lower stall torque, right? So it's not a very powerful motor at all. Okay? And there's a gearbox inside. Okay? So the issue with the gearbox, you can play around with it, right? Grab the bottom of the motor and move. move the pendulum around a bit, and you can see that it's moving without the shaft of the motor moving. And that's because of all the slop in the gearbox. Well, that's not going to be captured by our linear models, is it? Right? And it's going to make your gyro sensor on the pendulum arm see stuff that's not due to the motion of the motor shaft. Again, not captured by our models. These are all very non-linear effects, right, that are going to limit the performance that's actually achieved relative to what you've designed. You don't just have the gyro sensor to measure the angle of the pendulum. You've got an encoder in the motor. That's not going to see the slop. So consider using the encoder in the motor as the sensor rather than the gyro. See what the difference is. Okay? It's intentional, right, to not have these things perfect. It's so that you can appreciate that there's a difference between the real world and models. That's not to say that models are useless. They can guide design decisions, right? But there is a difference between the real world and the models. Okay, so there's no point in hiding that from you. Okay, so don't be surprised when the thing doesn't work perfectly, and if you do things in a silly way, you end up with limit cycle oscillations due to the nonlinearity. Try to figure out ways around it. For example, by changing the sensor. Okay, or using a different controller that doesn't require such a high gain. All sorts of things that can be tried. There's no one answer that we're looking for in the report for Workshop 4. What we're looking for is that you have explored use of the analysis tools that have been developed in the course to do a design. Okay? Make sense? Are there any questions on that? Now, the reason I'm emphasising this is because it's being fed back to me that people are looking for the exact answer. And I want to make it clear that there is no one answer. There are many ways to skin a cat, always. All right? Any questions on that? Yeah?
In this model, there are two codes. One is stable and another is...
Hang on, someone's asking a question. Don't speak over the top of them.
In this model, there are two codes of GS. One is
Yep.
stable and another is unstable.
Yep.
Why, if I create a CS in the new net to cancel out the unstable poles?
Oh, don't cancel unstable poles, ever. What happens if you cancel an unstable pole? With a zero of the... So you've got an unstable plant pole, right? And you put a zero in the same location in the controller, right? So that they cancel out. What's going to happen to the closed loop? Is the closed loop going to be stable or unstable? It's not going to be stable. One of the sensitivity functions, right, will have an unstable pole. If you cancel a pole of the plant with a zero of the controller, that factor appears as a factor of the characteristic polynomial. So if they're unstable, then your characteristic polynomial has a factor that is equal to 0 for a value of s in the right half plane. The zeros of the characteristic polynomial are the closed loop poles. So it's okay if you cancel them and they're stable, right? Then you're just saying, well, the closed loop will have a stable pole in that location, fixed. But if you've cancelled an unstable pole, then you're putting an unstable pole in your closed loop, which is not what we want, right? So you can't cancel unstable poles. Never, ever, ever cancel unstable poles. Putting that aside, do you really know where your unstable pole is? No, because your model's not right. Okay, so you won't even really cancel it. Okay, but you shouldn't cancel it anyway, because even if you could cancel it exactly, it will arise as one of the closed loop poles. Make sense? Any other questions on this stuff?
About this locus plot.
Yeah.
Why the circle will reach the depth?
Well, it has to at some point. Let's just forget about the extra pole that was put in to make the controller proper, right? Let's say, whoops, where's my pen gone? Let's say we've got this guy here, they're the plant poles, okay? We've put this guy in, all right? We know we have to put some zeros in to bring the relative degree down, because currently it's 3. And so there will be asymptotes that go into the right half plane. So if we pump up the gain too much, it'll be unstable. In fact, for any value of the gain here, will always be unstable, because when these two guys meet, they'll come apart and go along the asymptotes at pi and 3 and minus pi and 3. So we've got to put some zeros in, at least to bring the relative degree down, so that we don't end up with asymptotes in the right half plane. Okay? Let's put one here and one here. So this is like this literally is a PID controller, right? A PID controller has one pole, right, at s equals 0 and 2 zeros in the left half plane, right? That's this guy, the pole, and these are the 2 zeros. So, you know, the root locus rules tell us, well, the root locus will coincide with the real axis to the left of an odd number of poles and zeros, right? So this will be part of it, right? This won't be part of it because it's to the left of an even number. This will be part of it, right? Because it's the left of 1, 2, 3, that's odd, right? This won't be part of it because it's the left of 1, 2, 3, 4. This will be part of it, okay? How can this be part of it? Well, you know, this guy is clearly doing that, right? So how can we go from starting here, right, to ending up here, which is the only bit of the root locus that's left, right? Well, the only way that can happen is if one goes around this way and one goes around this way, and when they meet, right, they split apart again, and one goes towards the finite 0 and the other one goes towards the 0 at minus infinity. But if I put another pole in to make sure that my controller is proper, it won't keep going to minus infinity. It eventually will bump into this guy, which is moving this way, and then they'll split apart and go up asymptotes at pi on 2 and minus pi on 2 because the relative degree is 2. Make sense? Now, the exact shape here doesn't matter because I'm only using this analysis tool to give me a sensible controller structure. You know, if I'm okay, it'll look like this as long as the zeros are here and here relative to the plant poles and the controller pole at 0. Where exactly those are would have to be determined on the basis of more information, right? So we're just using this here to give us the structure. Relative to each other, where should I put the extra poles and zeros that I'm adding to the open loop transfer function via the controller C? Does that make sense? Yep.
I'm just not sure as to why it would occur that way rather than, say, for example, those two poles on the right plane, where they just go vertically up to infinity, and the left pole at 0, they just...
Hang on, which poles are you talking about?
So the right two poles...
Yeah. Oh, they can. They can.
Can't they just go up vertically and then the other two cancel out? Well, not cancel out, but like...
No, but you work out. If I put this pole sufficiently far to the left, this has to be sufficiently far to the left in order to make the asymptotes, these asymptotes, in the left half plane. You're right. If I don't put things sufficiently far to the left there, the asymptote won't necessarily be in the left half plane. But if I pull it far enough to the left, I can pull that in like that. Right? But it just involves pulling this sufficiently far to the left, right? If you think about what was going on here, where these ended up was really determined by this guy. And I can make these go this way by pulling this guy this way, right? So by adjusting the location of these, I can make sure that the asymptotes are there and not over here. I'm choosing this. I can put it wherever I like. Yeah? I could have put both zeros on top of here. Right? I mean, another way to do this, I mean, there is no unique way. You've got to understand that I'm trying to use the analysis tool to identify a controller structure, not the controller structure that might help me achieve my specifications. Now, engineering is not about plugging numbers into formulas blindly. Right? If that were the case, there would be no point in having you guys sitting in a lecture theatre learning about this stuff, because we could just write a computer program that's much better than a human being at plugging numbers into formulas. Right? Engineering is about making decisions on the basis of analysis tools, where the analysis tools might be applied in many different ways, right, to guide decision making. So what we're doing here is trying to decide what structure should I give my controller. How many poles and zeros should I have? Right? See what I mean? And I can make sure, to answer your question, that these are in the left half plane over here by pulling this guy sufficiently far to the left. You know, we could have done this, right? We could have just said, here's my open loop poles. Right, I'm going to put a pole at s equals 0 in my controller, right, so that I get 0 steady state error for step changes in the reference, for example. Let me put the zeros there on top of each other, right? And then, you know, if you look at where the anchor point is for the asymptotes, right, on the relative degree, right? Well, the relative degree now is just 1, right? You know, does it work? Well, I don't think it would work in this case, right? So, you know, it wouldn't work. We would actually have to, in this case, put another pole sufficiently far here to move the anchor into the left half plane. But this is all under your control. You're choosing this guy, these guys, and this guy. You put them where you want. They're not given. This guy is given, and the pole that's being cancelled here is given. Right? So you can get what you need by making the right choices. Once we've identified a structure that gives us the flexibility to make the right choice. Okay? So these are the sorts of things that you should be exploring in workshop 4. What we're going to do, which is not going to happen today, obviously, because we've spent a lot of time on this, but I think this is a useful discussion, right, is think about these sorts of design choices in terms of shaping the open loop transfer function, right, rather than thinking about the root locus plots, right? But, you know, there's no such thing as, you know, for problem A, you use tool A, and for problem B, you use tool B. That's just garbage, right? You use all the tools at your disposal when doing a design. So you might use root locus type analysis to say, well, a compensator with, you know, zeros and poles roughly in these locations will give me what I want. And then you go away, and now that the structure has been fixed, say, well, how am I going to choose the parameters there, the exact location of the zero and the pole and the amount of gain that I'm going to put in to give me the right loop shape across frequency? Right? So we're applying all the tools that we've learnt about to arrive at the final design in stages, where at each stage we're using some analysis to inform a decision. That's what design is about. I know this is a bit confronting because it's not the way you've been educated so far, but I'm trying to turn you into engineers, right? This is the way you've got to think. There is not just one answer. There are decisions that have to be made. You can, you know, do this to make a decision, but that's not what engineers do, right? That's the point I'm trying to make. So, are there any more questions on this stuff? Yep. Pardon?
Imaginary poles, which are like complex conjugate.
Yeah, what about them?
Something which is on the real axis
Well, let's say I had a system that had two lightly damped poles. Let's say they weren't in fact damped at all, the damping was zero. Let's say I had a system like this where the plant poles are like that. Is that what you're saying? Well, if I just use a controller that's a constant gain, what's going to happen? As I increase the gain, this guy's just going to move up like this guy's going to move up like this. The problem is we're stuck on the imaginary axis. What do we want? We want these things maybe going to the zeros at infinity somewhere in the left half plane. How can I make it happen in the left half plane? Well, if I use a controller that looks like this, right? These guys, the asymptotes, will now not lie on the imaginary axis, right? They'll lie somewhere in the left half plane. And this guy will go to this guy, and this guy will go to this guy, and this guy will go to this guy, right? Giving me, you know, potentially, depending on where I put this and where I put this, a well-damped closed-loop system, right? Again, what am I doing if you think in terms of Bode plots, right? My open-loop plant will be something, if it's got a pole here and a pole here, something that does this, and it'll go whoop, like this, and then come down at 40 dB per decade, right? So that'll be the magnitude of G. The phase of G, well, what's the phase of something that's got poles at plus and minus j omega? Well, there's zero. It's going to be stuck at minus pi, right? So no matter how much I scale the gain up and down of this guy here, at crossover, the phase is always going to be minus pi. Your Nyquist plot is always going to sit on top of the critical point -1 at some point, which is entirely consistent with as increasing gain with no compensator, without that there, these guys staying on the imaginary axis, right? Because there will always be a frequency, right, where we're sitting on the critical point -1. How do we fix that? Well, we need something that's going to give us phase closer to zero, right? Something that's going to bring the phase up. That's precisely what this does, right? So that when I scale the gain appropriately, I'll get a crossover frequency, say here, where there's a reasonable amount of phase margin. All right? Or you can think about it in terms of the root locus plot and how these move the asymptotes from sitting on the imaginary axis, in the case where the controller is just a constant gain, to sitting to the left of the imaginary axis when the controller looks like this with Z smaller than P. All right? But Z smaller than P is what's giving us the phase like this. The phase due to the plant is still this, but the phase of this is something that starts at zero, goes up like that, right? Which we then add to minus pi to give us something like that, so that when we adjust the gain to make the crossover frequency there, we've got some positive phase margin. Right, but from the perspective of the root locus plot, what's happening really is that when we're using this compensator, the asymptotes along which the closed loop poles approach zeros at infinity, as we increase the gain, move from being on top of the imaginary axis to somewhere to the left. So that as we increase the gain, these guys move to here. Right? There's just not one way of interpreting this, but each tool gives you a slightly different perspective on what's happening. And when making design choices, you want to take into account as many different perspectives as you can. So don't be looking for, you know, in this case I apply this tool and in this case I apply that tool. No, you've got a bag of tools, use all of them. Make sense? Yep.
How do you prove the transients?
Okay. Partly this is about improving the transients as well, right? Because the damping is going to affect how oscillatory the transients are. So transients is not just about how fast it is, how long it takes the transients to decay. It may also be about how oscillatory they are, right? So, if I make this, push this pole further to the left, I'll make the asymptotes move even further to the left of the imaginary axis, right? So in principle, for sufficiently large gain, I'll get faster, right? But to get there, I might end up with more oscillations because I'm increasing the imaginary part. So you can't just isolate different parts of the transient, right? But what we're talking about here is the transient part of the response. When we're talking about the damping, right, which is what we've been talking about, which relates to the phase margin, as we've seen, right, which relates to, how much the sensitivity function, 1 on 1 plus lambda, and complementary sensitivity function peak up, is about the transients. So all the stuff we've been talking about now is about the transients, getting the right sort of transients, well-damped transients. Yeah?
What else can be a trade-off? Can we say there's a trade-off
Between what and what?
between stability and transient improvement?
Well, I don't think so. You need stability before you can even think about transients, right? Because if it's not stable, there's not just a transient, the thing blows up. You only get a transient that dies away, leaving you with the steady state if the system is stable. So first and foremost, you need the system to be stable. Then you worry about the transients. And so that's like choosing, well, how big a gain do I have? Do I choose the gain so it's here? Or do I choose the gain so that it's here? And there you're making a trade-off. So I know I'm choosing the gain so that it's stable, because the closed loop poles are in the left half plane. If I choose the gain here, gain such that the closed loop poles are here, then I will get, a response with transients that decay, at a certain rate, okay, with oscillations corresponding to this frequency. If I choose a higher gain, I might make the transients decay faster because I'm moving further away from the imaginary axis, but at the same time, I increase the frequency of oscillation. So what's more important? Well, it depends on the application. So it's not a trade-off between stability and transients. You need to establish stability, because without stability, the word transient doesn't even make sense. Right? There's only a transient part and a steady state part for a stable system. If it's an unstable system, I kick it, it blows up. There's no transient that dies away, it just blows up. Right? So you need to first establish stability. Right? And then I still need to choose. Do I choose the gain that puts the closed loop poles here and here, or do I choose it so it puts it here and here? Well, choosing it so it puts it here and here makes it faster than putting it here and here. But the price I'm paying for make it faster in this particular case is that I end up with higher frequency oscillations. What's more important? Well, it really depends on the application. But you would have to make a trade-off against those two aspects of the transient response in this case. For different systems, it might change, right? When we've got this sort of thing here, choosing the gain to put them here, right? Or I could choose the gain to put it here. In this case, choosing it to put here both makes it faster and reduces the frequency of oscillation. So it really depends on the setup. There's no one rule, right? Surely it's better to understand how these things work so that you can apply them in many, many different contexts, rather than trying to remember, in this situation I should do this, and in this situation I should do the other thing. That's a bad way of thinking. It's a very limited, narrow way of thinking. Have I answered your question? Yeah? Okay. All right, we'll leave it there for today. We'll still look at problem set 4 tomorrow.
Question about the first plan. Yeah. we talk about when we look at this body part, we see that we have two poles, one is stable and one is unstable for the plant. And
Well, that's why we start at minus pi. We start at minus pi because of the unstable. If I have an unstable pole, so if I look at the phase of 1 on S minus P, that's unstable. The phase, what will the phase look like?